Yes, thank you very much for having me here and giving me the opportunity to present this exciting research that hopefully will invert you to do everything with invertible networks. So this is, of course, work by a big team. Lyndon is sitting here in the front, so he can answer all the real questions. And several others of the team are also here, and I would also like to appreciate the joint work with Lena's team, and Tim Adler did the hands-on work. So first I would like to show shortly what problem we are addressing. So we have some unknown true data generating mechanism. So y is sampled from some true conditional probability of y given x. And what we would like to do is to find an approximation of this p star, which I call q star here. And this should be the solution that minimizes some loss function. And the solution must come from some family of solutions that we, as designers of the algorithm, choose. So, for example, L2 loss or something else. And first, I would like to simplify a bit. So P star is now not a probability distribution, but a deterministic function, G star. So only one possible outcome. And I would like to show some very important error sources. So first of all, if our model family is too small, then the true function G star may not be in F. And then we get a best possible approximation F star. And if the family is too far away from G star, then we get a big model's misspecification error. Yeah, so the function f star will not explain very well what G star does. So this has become less of a problem with the introduction of very deep neural networks. So then the model family is usually big enough, or at least close. So then the epistemic error means that we can never know f star precisely because we only have finitely many training data. Yeah, and so the function f tilde that we actually get from the training data will not be exactly the one that we would get with infinitely many training data. So then the optimization error means that we may not be able in practice to actually find this minimum here, so the solution that minimizes this loss. So for example, it may be NP hard to find this solution, yeah? And then we have some optimization error, so we only find the mean of some algorithm and not the true mathematical mean. So these are three common error sources. Okay, but in the probability case, so when this is actually this probability distribution or density, then we also have an aleatoric error. So the observations x and the mechanism that maps x to y's may be noisy. And then we do not always get the same solution. And in classical machine learning, it's usually reduced to the deterministic case from the previous slide by just taking the expectation, which is then a deterministic function, or the maximum a posterior solution, which is also a deterministic function. Yeah, and then we have the ambiguity error. So X may not contain enough information to fully recover Y. So that's the case that's most relevant for inverse problems. Yeah? So Y is the thing we are actually interested in, and X is what we observe about Y. And it may just not be enough. And then we have an ambiguity, so several y's are compatible with x. And this can be reduced to the deterministic case by adding additional constraints, for example, regularization. Yeah? But then, of course, instead of getting many possible solutions, you just get one, and that may be the wrong one if the regularizer picks the wrong solution among the infinitely many. So, and in Bayesian statistics, you do not do these reductions to the deterministic case, but you actually want to determine a good approximation for the full posterior probability. Yeah, so that the ambiguity and the aleatoric error is properly modeled. The problem with Bayesian statistics is that it's hard to find a family of functions for Q star where actually the problems of interest are in. And this has really only been solved to a degree by neural networks. And on the other hand, classical solutions like Monte Carlo solutions, Markov chain Monte Carlo are very expensive, so they can do this, but they take forever for interesting problems. And we look at what neural networks can offer, and specifically at the problem of inverse problems. So here we have some forward process. So the forward process, unfortunately, now the rows of x and y are exchanged in relative to the previous slide. So we have some system with an internal state that's described by some vector x, and x is hidden. So we would like to know it, but we cannot see it or measure it. Yeah, and then there is some physical or psychological or whatever mechanism which gives us variables y, which we can actually measure. Yeah, so this is the forward process, like from x to y. You see here already the problem. Many different, two different x here, and the diagram map to the same y, and here two different x map to the same y. That's the ambiguity. Right? We don't know which x the y came from. And here is the inverse problem. So now we are given the observation and would like to find out what x was. And here are two possibilities. So here in the lower arrow, we just select one of the possible solutions. This was, for example, the argmax of the previous slide. Yeah? And the other possibility is denoted here. We take the average of two. That would be the expectation case of the previous slide. Yeah? And of course, in the first solution, we entirely miss the fact that there is another possibility for x. And in the second solution, we get some average that may not even a legal value for x. Yeah? And this is a big problem. So in order to motivate, so this is ubiquitous in science. So in physics, for example, crystal structure is investigated by X-ray diffraction, and then you have some diffraction patterns and need to figure out what the crystal was. Yeah, or we will see the greenhouse gas concentration example later in the talk. Then from tomographic, what's called xenogram, we can reconstruct 3D tissues, or that's a, if you want to dig for water or oil, then you have some wells where you know there is oil or there's no oil, and you would like to know where to bore the real hole, right? So, first to simplify for explanation, takes long. Here's a very simple version of the inverse problem. So let's see, say x1, x2, x3 are the hidden state that we would like to know, and they are all sampled from a standard normal. And the observations arise by this linear equations. So y1 is x1 plus x3, and y2 is equal to x2. So we can reconstruct x2 from the observations, but we cannot reconstruct x1 from the observations. In matrix notation, that just looks like this. And then you see that the matrix A is non-invertible. So we would like to find all the y's that satisfy, all the x's that satisfy this linear equation. And this is an ill-posed problem, so we have infinitely many solutions. And of course, here in the linear case, it's easy to solve. So for example, if one wants to reduce this to a deterministic thing, then one would determine the null space of the matrix A and then choose one solution which satisfies the regularizer from the null space. So, and the Bayesian approach would give the probability distribution of all possible answers or a sample from that probability distribution. Yeah? So if we are not able to find a formula, then a sample is the second best option. So here is the solution idea. We construct an augmented observation space. So here's now a new variable, Z1, which in this case is defined as the difference between x1 and x3. And then we get the linear equation A augmented times x. And this matrix is now invertible, and we can just compute x by multiplying the augmented observation with the inverse matrix. Yeah? That's easy. The only problem is, of course, that we do not know z. But we can easily compute the probability distribution of z because it's the difference of two Gaussians. It's a Gaussian with twice the variance, so that's very simple. And then we can sample z1 from that distribution. And for each sample of z1, we get one solution of x. And then we sample another z1 and get another solution of x. And then we repeat this until infinity, and then we get the full distribution of x. Yeah? So this is the general approach that we now want to implement for the general case of nonlinear mappings. So here, this was the linear case, and now we have some unknown function s of x, which is nonlinear. And the inverse function s inverse of y does not exist or is ill-posed, yeah? Ambiguous. Now we do the same thing. We find a vector z that creates this augmented observation space and an augmented forward mapping. And we arranged such that the y part is the same as before, and the z part here follows some known distribution where we can easily sample from. So that's the same thing as we sampled the z on the previous slide. Yeah, and then we do the same thing. We can invert the augmented function because it has been constructed to be invertible. And then we sample a z, insert our actual observation, and then we get a sample from x. Yeah, so now we want to implement this. These are two conditions. So the new function must be invertible, and z must be independent from y, so that we can just sample z without considering what the current value of y is. So now we would like to implement this with neural networks. And here's a schematic. So this was the original problem. This is the augmented problem. And now we would like to learn this part here, the bijective mapping with a neural network. And since it's a bijective mapping, the obvious choice is to use an invertible neural network. Yeah, and invertible neural networks can run forward and backward, and both in the ideal case are equally fast, both passes. And as a bonus, many types of invertible neural networks have a tractable Jacobian, so it's the derivative matrix, so that we can, for example, do maximum likelihood training or can compute exact entropies and things like that. So that's a big advantage. So now, why is it so slow? I'm not sure whether I have already pressed or not. Yes. So our favorite design is what's called the real NVP, real non-volume preserving architecture, which was published in 2017, which is a sequence of coupling layers. So this is how a coupling layer looks like. So here's a network with just one coupling layer. X goes in, Y comes out. But one can stack many of these behind each other to make a deep network. So each coupling layer splits the input into two parts. So the first half of the variables and the second half of the variables. And then the output, likewise, is concatenated to form Y. Yeah? And in the middle, the both halves are subjected to some affine transformation, where the coefficients of the transformation depend on the other half. I will show this in an animation on the next slide. So the forward computation is, so this is pointwise multiplication by S2 plus some translation. And here the same thing. And you see, since this here depends on the result of the first transformation, we can solve these two equations for x1 and x2 and get these two equations. Yeah? So it's just the inverse of a linear function. And this is the forward computation. This is the inverse. So let's look at what this means. So this is the coupling layer. So we split the input into two halves. Then we compute pink coefficients or purple coefficients from the second half. Then we use the purple coefficients to compute a red result for the upper half. And we use the red result to compute orange coefficients. And we use the orange coefficients to compute the red result of the lower half. And then we put everything together, and that's the output, yeah? Concatenation. And the backward pass just reverses the arrows, most of them. So we split the input from the right-hand side. Then we compute orange coefficients, use the orange coefficients to transform the red back into the green. Then we use the green in order to compute purple coefficients and use the purple coefficients to compute the upper half red into green. And then we concatenate everything and get our original data back. Yeah? And the crucial thing about this design is that these nested functions, which are also neural networks, so the S1, S2, and T1, T2, are in both cases run in the same direction. Yeah? The entire network runs forwards and backward, but the nested networks run only in one direction, so they don't have to be invertible. And that's the main trick of the method. So they can be arbitrary complicated networks and standard CNNs, for example. So in reality, it turned out that we should use only a half coupling layer. So only one half of the data is transformed. But we stack many of them together. And in between, we have orthogonal transformations, so coordinate rotations, so that what's the upper half changes from layer to layer. Yeah? So that all data are properly mixed with each other. And then we can have up to how many layers, Linton? 100 or so. Okay, so now I have already shown this slide about the general approach, and now how does this work with the invertible neural network? So this forward process is now the mapping that's implemented by the neural network. the agreement of the y part is enforced by minimizing some loss on the y part. And that z follows a known distribution is enforced by some loss on the z part. And that this function is invertible is automatic because we designed our neural network to be invertible. And this independence is also enforced by this loss on z. So now the training, the total loss is a loss on all three sides where the x loss is optional. So when we have it, it usually converges faster, but it's not strictly necessary. So Ly matches the output to the training data. That's what ordinary neural networks always do. Yeah? And z matches the z output to be a standard normal distribution. And Lx matches the backward pass so that the generated data look like real data. So that's very similar to a gun, for example. Yeah, and here are the loss functions that we initially used. Right. In the meantime, we have tried many different possibilities. So this is just L2 loss on y, and this is what's called the MMD, the maximum mean discrepancy. Is used to compare two batches of data, u and u prime, which are drawn from two different distributions. And the paper has proved that this MMD is asymptotically zero if the distributions are actually equal. Yeah, and positive if the distributions are not equal, and it's just a kernel. So the expectation over kernel outputs, and we use the multi-quadratic kernel. So then we have trained the whole thing. Now we would like to do inference, and as I have already explained, the backward process is implicitly learned because the network is invertible. And given an observation, y hat, we sample some z and compute x hat. And then x hat is unique because was z, and that's the point of it, is trained to provide all the information about x that has not made it into into y. Yeah? All information that is lost about x is collected in z. And that's why the whole thing is invertible. Yeah? And then we repeat this several times. So we sample many z's, and then we get a sample of x's. And we can prove if the losses are actually zero, which of course never happens in practice, then the sample of x hats follows the exact posterior that we wanted to learn. So right now, an open problem is how close to the true distributions we are if these losses are non-zero. So now a toy example, inverse kinematics. So we have designed a little virtual robot arm. So the robot arm can move up and downwards here on the dotted line. And then it has 3 joints where it can rotate in 2 dimensions. Yeah, so that's in total 4 degrees of freedom. And then we have the hand. And the hand position where the robot's hand lands is the y variable. Yeah? X is the position of the arm and the joints, and y is the hand position. And then we have a prior so that the arm likes to be straight. So that's the region where the arm likes to be, or the hand likes to be, wants to be. And we want to learn the forward mapping, where z collects all the information about x that's not determined by the hand position. Because obviously, many different arm configurations land at the same hand position. Yeah? And then we can fix some hand position here and invert the whole thing and find out how can we configure the arm in order to reach that desired hand position. Yeah, and this problem is interesting because it has a bimodal nature. So there are two distinct possibilities of solutions. So we can either grasp downwards or we can grasp upwards, but we cannot grasp through the middle because then the hand is too far. Yeah? And classical regularizers would just find one of the two possibilities and not both. So here is the lower and the upper arm position and the very unlikely middle position, because here we have a very high angle which the arm does not like. So here are two solutions. So the left is a very expensive ground truth by rejection sampling. So we tried millions of arm positions until we had a good collection of positions where the hand was at the desired location. Yeah? And this is the output of one of our networks. So, and you see two things. So first of all, it finds the two possibilities. Also, it has a bit too many in the middle. Yeah? So it's not exactly equal to the ground truth. And then there's also an approximation error. So when we insert the estimated x from the network into the simulation, then the hand does not exactly land at the desired position due to approximation errors. And this is the region where the hand lands 95% of the time. And this should, of course, be as small as possible. Down here are other examples which are easier configurations because there's no bimodal distribution. Yeah? So before I continue with this example, I will tell you a bit about possible designs for invertible networks. So I already explained the real NVP. Autoregressive flows are essentially networks where we have only one very big triangular layer, yeah, invertible layer. This makes them relatively expensive in comparison to the real NVP, but they are, for example, used in the famous parallel wavenet speech recognition and generation system. Yeah? So then we can also give up the invertibility by construction and use just asymptotic invertibility, which means that after infinite training time, the whole thing becomes invertible. So, and an example is the autoencoder or the cycle gun, where we have additional cycle losses. Yeah? And once the cycle losses become zero, we know that the encoder and the decoder are inverses of each other. Yeah? They usually don't have the tractable Jacobian, so they don't support maximum likelihood training. And then another one is what's called the IResNet, which I mainly show for the physicists because it's closely related to differential equations. Are there any physicists here? Okay, so I can continue. So what we do here is L is the layer number, the layer index. So we have the input of layer L, ZL, and the output of layer L, ZL plus 1, and then we add the output of the neural network. Yeah, so the neural network just models the residual, the difference between ZL and ZL plus 1. Yeah, that's why these guys are called residual networks. Yeah, and if the derivative of this, or the norm of the derivative of this guy is restricted to 1, then the whole thing becomes invertible. So it doesn't mean that inversion is exactly cheap, but you can do this, for example, by a simple fixed point algorithm that runs for 20 iterations or so, and then you get the inverse. So, and this is not so interesting. Here's the relation to differential equations. So the residual network has fixed time steps. So these are the layers. Layers could be also interpreted as time. Yeah? And then the network just learns the increment from time step to time step. And that's the same thing in a differential equation. So we have here discrete time and here continuous time, and the time derivative is the right-hand side of the differential equation. And the advantage, if you do this way, is that you can use adaptive time steps, whereas here we have fixed time steps. Yeah? And you could have small steps when there are many changes and big steps when there are little changes. So this is a very interesting line of research in this whole area. So here are some network types that we compared. So our invertible one, then the conditional INN that I will show later in the talk, an invertible autoencoder, invertible residual net, that's the one I just showed on the previous slide, the autoencoder, the conditional autoencoder, and the autoregressive flow. Yeah, and then a traditional mixture density network, which is not invertible, but which serves as a kind of baseline. So, and then applied to our robot arm, we see that the INN results are the most similar to the ground truth. Conditional INN is also quite good, not quite as good. And then the autoencoder also has the bimodality here, but the invertible ResNet did not find the bimodal distribution, so that's surprising. Maybe we can now train it better and find it anyway. Here are the numbers. So the errors here of the invertible networks are the best, and the autoencoders are also quite good, but have a much bigger spread. And then the baseline, the MDN, which is not invertible, is also very good in this particular application. So now for a real application, which was done together with Lena's team. So in a minimal invasive surgery, we have an endoscope that looks into the body, a camera essentially. And then before we cut into any tissue, the surgeon must make sure that the blood flow has been interrupted. Yeah? Otherwise, the operation will end in a mess. And what they do is they set little clips here. It's hard to see. And if the clips are applied properly, then the blood flow should stop. And then this should be seen in a false color images like this. The blue is no blood flow and the red is still blood flow. Yeah. And here, what turned out to be necessary is to use a multispectral camera, and then the observations are the spectrum, so RGB channels or 8 channels or 25 channels, depending on your camera, and then the unknown state X is, for example, the blood oxygenation. And the forward process has been implemented as a Monte Carlo simulation, which I explain on the next slide. So here, there is a set of tissue parameters like oxygenation, but also tissue thickness and scattering parameters of the tissue. And then the simulations is essentially ray tracing. Yeah? So you have some rays and they are scattered and absorbed, and then eventually they escape from, and it gives you this spectrum. Yeah? If you repeat this with many, many rays. And then you can discretize the spectrum according to the properties of your camera, and that's your observation Y. And now the task is to come back to X from Y. So, and what we want is, given Y, sample some Z's, and then compute all the compatible X's with this Y, yeah, as I explained earlier. And it turns out that this works pretty well for blood oxygenation. So here are the results. So this is, again, this very expensive rejection sampling ground truth. Then this is our solution, and these are two other common networks. So for example, a Bayesian network with dropout inference and a conditional variational autoencoder. So, and we see a number of things. So first of all, the blood oxygenation is pretty well found by all the methods and with pretty small standard deviation. Yeah, then the volume fraction, so how much blood is in the tissue, has been found very well by the ground truth and by our method, but the other methods always return a symmetric distribution, whereas the fraction cannot be more than 1. Yeah? And so we have a skewed distribution. And then here, this is especially interesting. It turns out that the gray stuff is the prior distribution and the blue stuff is the posterior distribution. So, and the posterior distribution is the same as the prior, which means that the data have not given us any information about this parameter. So this parameter cannot be recovered from a spectrum. So here it's much more noisy because the rejection sampling just didn't have enough samples to recognize a uniform. But here you see they have still a Gaussian distribution. So they think that this is the most probable value. There's a big standard deviation, but still, so it's overconfident. Yeah? And that's the kind of advantages that we find with our posteriors. So then, same thing here with correlation. So we find the correct correlations between parameters, whereas the other methods can't. Another application, which camera should one use for this problem? So there are 3 candidates, 3 spectral channels, so usual RGB camera, and then 8 or 27. And this is, of course, hugely expensive. So you only use this if you have to. And then we trained, or Tim Adler trained the neural network with these 3 variations. And then what came out is that, for example, in this output, there is a B-modal posterior. So the most likely mode is the wrong one. So the second best is the correct one. And that's, of course, something that you do not want, right? You want the most probable solution to be the true solution. So that's not what we want. Or here, the solution has a high variance. That's also not what you want. And this is okay. So close to the truth and small standard deviation. And then it turned out so that you can achieve this with the 8-channel camera, but not with the 3-channel camera. Okay, so this concludes the first part of the talk. So the plain invertible neural network, and now comes the conditional one. So far we have augmented the observation space with additional variables, and this does not always work. And here we have an alternative design. We map X to Z, and X and Z have the same dimension, which is wrongly drawn in this picture. And the condition Y, so the observation Y, just changes the parameters of the network. So in a sense, for every Y, you use a different network. Yeah? And then that means a different mapping between X and Z. That's how it looks like. So this is the same coupling block as before, but here comes in the condition. Then there's some feature detection in the conditional variable. So this is necessary if the conditional variable is very big, like an image, as we see later. And then the features are fed into these S and T networks and modify the coefficients of the transformation according to what the condition requires. Yeah? And then what we can do is we can simply input the condition, again, input the condition here. sample from Z, run the network backwards, and get a sample from X, and then repeat this many times. So I will skip this. So this is the forward pass. So in the forward pass, we take the true observation, because we have training data, to transform X into Z's and make sure that the Z's have the desired distribution P of Z. And in the backward pass, we take and here we use the true X and the true Y from the training data. And now we only have the Y, the observation, and then we sample from Z, run the whole thing backwards, and get a sample from the posterior distribution of X given Y. Yeah, here's a nice application, colorization. So we have given grayscale images, 256 by 256, which is just the luminance channel in the LAB color space. And this is an example image. And the problem is, the task is we would like to recolor this image. Yeah? So, and the colorization should be realistic. So this is our inverse process. Of course, creating a grayscale image from a color image is easy. Everyone can do that. But the other way is difficult. And the second requirement is that we do not just want one color image, but when we sample different Z, we want also different X, so different color images. And they should be as diverse as would be natural. Yeah? So these are 9 images. And now comes the quiz. Which of these 9 is the true one? Yeah, so maybe we have a biologist who knows this bird. So I give you a joker. So it's one of those. So who's for the top one? Who's for the middle one? Who's for the lower one? So everyone has already seen my talk, so that's correct. So I think we need a new quiz image. So here's how it's implemented. In this case, because we are talking about images, we use convolutional coupling layers where the S and T networks are CNNs. Yeah? Everything else is the same. And then we have many of these layers, and then we have also downsampling layers so that split off the high frequency information from the image, the details, and only the big stuff is further processed at the next resolution level. And then from top, the gray level image, which is the condition Y, is fed into H, which detects features, and then further fed into these small networks, which adopt the features to every layer and then control the convolutions in this layer. And then the last stuff are fully connected layers. So it's a pretty standard architecture as you would also use for classification. But instead of normal convolution and downsampling layers, we use coupling layers. Yeah, so that's. And then here's how the downsampling works. So we apply a wavelet transform and only keep processing the average channel of the wavelet transform. So here are some more examples. So on the left are the grayscale image, on the right are diverse colorizations. So here, even more examples. So you also see it's not fully perfect here. The color of the mushroom is a bit inconsistent, which is always one of the failure cases of colorization algorithms. Yeah? And the other failure case is that the color leaks out into the background. So if you want to see the failure cases, you need to look into our paper. So this is how the latent space Z behaves. So this is the standard colorization. And then with some Z, and then we downscale the magnitude of Z. Yeah, and this takes away the color. But it doesn't result in a gray image, but it results in some kind of a default outdoor nature image. So it's like a bit greenish brownish, right? And the other way around, if we have make Z bigger, then it's overcolored, so oversaturated. Yeah? But you see the interpolation from 0 outwards in the latent space just enhances the color, but the colors themselves are consistent. So here's another application, which is color transfer. So we have a grayscale image, and we would like to color it like some other image. So it should be colored like this car, and then we get a blue car. Or it should be colored like this car, and we get a green car. So it's not the same green, because this green is not compatible with the gray image. So it has to modify the green a little bit. So here's a real application in environmental physics. So this is the rays of CO2 concentration in the atmosphere. So this zigzag is the yearly periodicity, and this is the rays. And this should be measured from a satellite. On the satellite sees spectra in various bands. Yeah? And given these spectra, we would like to recover the CO2 concentration. And we do essentially the same thing. So our X is the CO2 concentration and a few other parameters that are also of interest. And the input is the spectrum and the location of the satellite and time of the image, because that's important for the lighting conditions. Yeah? Because the spectra, of course, depend on where the sun was. And also some meteorological parameters. And then we train a network. And this is possible because the environmental physicists already have a physics-based simulation for the backwards pass, but this is expensive. So our networks is 1,000 times faster and not quite as accurate, but pretty good already. So here are the arrow bars. The green ones are the arrow bars. The blue ones is our distribution, and the red one is the truth for some test set. So now the newest incarnation of the invertible neural network is what we call the Latent Mixture INN. So far we have seen the Conditional INN, where we map from X to Z, conditional on Y. And the mixture one gets rid of the Y, and the Y only works on the structure of the Z distribution. So Z is now no longer a normal distribution, but a Gaussian mixture model. And we have one mixture component per conditioning value. So the easiest to understand this is that Y are class labels. Yeah? Like in MNIST, the digits we will see on the next slide. And for every digit, we have one Gaussian distribution. And all of them together form a Gaussian mixture model in Z space. And the cool thing about this design is that under suitable conditions, we can prove that the latent space gets disentangled into meaningful features. So usually in an autoencoder, the Z's are just numbers that you cannot interpret. But here in this design, the Z are actually meaningful variables. And we see this if we look at MNIST. In MNIST, we have found 22 meaningful variables. And all the remaining 762 are just noise variables. So if you have high values in these variables, you will just get noise. Whereas high value in the first 22 gives you meaningful variation. So the variable 1 varies the upper width of the digit. Yeah, so the lower width is essentially constant, but the upper width increases. And then variable 8 takes care of the lower width of the digit. Yeah, and this is new. So in previous work, people already have found a variable that controls the widths, but our method says that it's actually two independent variables that control the upper and the lower widths separately. Or here, the height. So as we increase this variable, the digits become higher. And that's, as far as I know, a variable that had not been found in previous work. So, and then the first 8 or so, or 10, take care of global variations, and then the remaining ones take care of local variations that, for example, only apply to particular digits, because other digits do not have the feature that is being varied. And the most extreme is this one, this variable 16, which only varies the tail of the 2. So everything else remains the same. Yeah, so you can, if you imagine the 2 to be a cat, then the cat wags her tail. Yeah, and this is a very interesting model that we are currently pursuing and try to get applied to many different questions. So that's the talk summary. So I have shown you 3 approaches to solve ill-posed inverse problems. So first, the direct approach, where we learn this augmented space, where y corresponds to the true distribution of the observations, and n is a standard normal. Or we have the statistical approach, where z is learned and y conditions the network. And we have seen the latent mixture approach, where the network just depends on z, but then the output is a mixture with mixture weights, the prior of y, and then the Gaussians for every class. Yeah, in all cases, we get full posteriors and learn a space z, where we can sample from, generate data. Future work, some of it, we would like to enhance this latest achievement, so the disentanglement, so to real problems. MNIST is just a toy problem, right? Also, if you have the opportunity to measure y multiple times for the same x, then you would like to get the posterior distribution of x narrower and narrower the more y's you have. Yeah, as in classical Gaussian approaches. It's called posterior contraction, and that's not something we have yet achieved. Then we would like to extend it to the unsupervised setting. For example, in the MNIST example, we had to know which digit each picture is, and we would like to get rid of that. And of course, we would like to apply this to real important problems and not just toy problems. And that's where we invite all of you to collaborate. And finally, I would like to thank the team. So these are the people in our lab that have contributed to this work. And then Lena's team has done the application with the blood flow. The Institute for Theoretical Astrophysics applies it to astrophysical inverse problems, for example, understand star formation, and environmental physics, as I showed, with the CO2 concentration. So thank you very much. Questions?
Great talk. I have one question regarding the latent mixture INN. You showed in the MNIST data that when you look at the latent space, the first latent variables they seem to recover global patterns of variation, while as you go down the hill, you sort of get to the more granular case-dependent examples. Have you tried this in other data sets and sort of recovered similar patterns where you sort of first feature cover the majority of the variance and then you sort of go down in terms of variance towards more local patterns?
Not yet, so that's work in progress. But since it's supported by some theory, so when the assumptions of the theory are fulfilled, it should always work. only that we do not know and we cannot check in real data whether the assumptions of the theory are fulfilled. More questions?
Wonderful talk. So how long does it take to train your data?
Typically similar to ordinary neural networks, I would say. Yeah?
For the science applications, a few hours. For the images, a week or 2 weeks. Yeah, for the colorization.
On what system are you simulating?
No, it's just
So the blood flow can still be done on a desktop GPU, I would say, but for the image stuff, you need parallelization on several GPUs. But it's about the same amount of time that, for example, VGG required to be trained on ImageNet if we apply it to ImageNet as well. So it's comparable.
Thanks for the talk. Do you have any idea how well or if that method is more robust against errors in ground truth or less robust than conventional methods?
Maybe Lyndon can answer this question best. So, I mean, it's certainly robust to some label noise, for example. Yeah, and then what we found also is that the invertibility requirement is a very strong constraint. So it's, for example, mode collapse or things like that cannot happen or not as easily. And then I hand over to Lynn.
Yeah, so just keep your eye on our website, and maybe in the next couple of weeks, something might appear.
So there was another question somewhere there. Mm-hmm.
So if you take a neural network and you put it into this architecture to make it invertible, how do training numbers compare? So do you need more training instances to get same results, or less? Does it have any effect? Just the same?
Yeah, so I mean, in the MNIST disentanglement example, we found that there is a variant of MNIST called eMNIST, which contains just 4 times as many digits as the ordinary MNIST, and then in addition it also contains letters. And we found that on the eMNIST dataset, it found better variables in the Z-space. So because there was more variation in the data, so that could figure out which axis of variation would make the most sense. But otherwise, so I mean, it's a more difficult problem than just predicting the digit, right? So if it needs more data, it's not really very surprising.
You mentioned that for the MNIST, a lot of the variables are just modeling noise.
Mm-hmm.
Is there a way to get rid of those variables, or are they fundamentally necessary to go a simple way that you specifically want to map the observations?
Yeah, so this is a fundamental property of invertible networks, that the Z-space must have the same dimension than the X space. Yeah, otherwise the function will not always be invertible. But the cool thing is that in the Z-space, we can arrange for the first few variables to be the important ones, and the remaining ones to be the unimportant ones, and then we can just set them to 0. So for example, if we would use that for compression, yeah, we would just transfer the first 22 dimensions to the other side, and then decompress only the first 22 dimensions and just throw away the others. So we need to compute them, but we don't need to keep them. And of course, we could also come up, once the network has converged, with some pruning algorithm that would prune out the unneeded neurons somehow. But we have not tried this in practice.